Welcome to this session for the School of Computing at University Utara, Malaysia. I'm Dr. Ala Jabbar Al-Maliki. Today, we are examining the absolute baseline of network security. We spend countless hours discussing cryptography, software firewalls, and malicious code. But every line of code, every virtual server, and every encrypted packet requires an unbroken chain of physical engineering to exist. Look at the standard OSI. Layers like application, transport, and data link dominate our attention. But strip them away, and you are left with layer 1, the physical layer. A mathematically flawless encryption algorithm cannot function if the server rack loses power. A perfectly configured firewall protects nothing if the routing hardware is destroyed. True network defense requires treating physical cables and power grids as the ultimate point of failure for all logical computing. In traditional military strategy, kinetic warfare is divided into two categories. Direct fire involves using line-of-sight weapons like main battle tanks to apply immediate physical force to an objective. Indirect fire involves assets like artillery or overhead aircraft formations that project destructive power over large distances, bypassing immediate defenses. Cyber warfare employs exact equivalents to these kinetic weapons to achieve a physical denial of service. Precision direct fire tools like wire snips are used for surgical infrastructure attacks. Blunt indirect fire tools, such as industrial backhoes, are capable of massive, localized infrastructure destruction. An adversary has zero need to bypass your network security protocols if they can walk outside and physically cut your data center's connection to the global internet. Physical attacks typically target availability, while assaults on hardware or the theft of components compromise confidentiality. Beyond blunt force, data centers face non-kinetic threats.
Our reliance on dense microelectronics creates massive vulnerabilities to electromagnetic attacks. An invisible wave of energy can instantly overload and fry thousands of circuits. Media often portrays the electromagnetic pulse, or EMP, as a magical catch-all weapon. Engineering reality requires us to separate this fiction into two specific threat categories. The first is a high-altitude electromagnetic pulse, or HEMP. This is generated by detonating a nuclear weapon hundreds of miles in the atmosphere. The resulting energy wave blankets a massive geographical area. A HEMP event indicates a severe global conflict. It would trigger the sudden collapse of civilian power grids, communications, and transport networks across a continent. Contrast that with a high-power microwave, or HPM. Generated by chemical explosives or high-capacity batteries, an HPM focuses its energy on a highly localized target. While a HEMP destroys entire regions, targeted HPMs pose a much higher daily threat to specific data centers because they are incredibly difficult to harden against. Electromagnetic disruption paralyzes the signals those hardware components rely on to communicate. State militaries deploy sophisticated electronic warfare devices to blind radio, radar, sonar, and infrared systems, shattering their ability to transmit or receive data. Beyond military-grade technology, we must account for the asymmetrical threat of civilian-level jamming. Everyday electronics, including modified cellular phones or microwave ovens, can be weaponized to disrupt frequencies. The schematics for building custom jamming devices are readily available and easily accessible online. The barrier to entry for electromagnetic disruption is low, allowing unsophisticated actors to execute highly damaging data denial attacks. Defensive strategy relies on a dual approach, fortifying facilities to withstand assaults and building redundant infrastructure to survive a breach. Layer 1 is perimeter security. Physical barriers, force protection, and security personnel ensure that physical threats cannot easily access critical infrastructure. Layer 2 introduces Tempest standards, or telecommunications electronics material protected from emanating spurious transmissions. A Tempest-certified structure incorporates blast hardening and specialized metallic shielding built directly into the architecture. This deflects external electromagnetic assaults, like EMPs, protecting the fragile servers inside. This shielding also traps internal electronic emanations inside the facility, preventing signals from leaking out where they could be intercepted for espionage. True data confidentiality relies just as heavily on the metallurgical properties of the facility's walls as it does on encryption algorithms. Even with physical perimeters and heavy shielding, a defense-in-depth approach requires systemic redundancy to ensure functionality if part of the network fails. This requires uninterruptible power supplies, backup generators, and alternative communication channels to maintain continuous connectivity. The human workforce and their adherence to Operation Security, or OPSEC, remain the most vulnerable layer in any physical security matrix. If personnel casually discuss infrastructure in public or fail to protect sensitive documents, they completely bypass millions of dollars in physical hardening. Robust OPSEC requires personnel to embed continuous risk assessments into their daily routines to maintain security awareness. As students of computing, you must remember that resilient architecture is a triad. It requires secure code, fortified hardware, and disciplined operational procedure. Without all three, the network is vulnerable.